there's a term that we use all the time. This term is called the bound state. And a bound state seems something sort of very non-trivial, but mathematically we can say quite clearly what it is. A bound state is something that is not spread all over space, basically. And the way we therefore use the terminology of a bound state is that we only speak of bound states when there are energy eigenstates. So an energy eigenstate may or may not be a bound state, but any bound state is an energy eigenstate. So an energy eigenstate is a bound state if the wave function goes to 0 when you go sufficiently far away. So it's a simple definition, but it helps us understand that the basic idea is that the state is just not spread all over the world. Now, remember, we're trying to find energy eigenstates, and that is to find wave functions, time-independent wave functions that solve the time-independent Schrödinger equation, which I have rewritten there for convenience. This is the same equation we wrote last time for a time-independent potential, so that the full wave function can be written as a phase that contains the information of the energy times a function of x, psi of x. That still may be complex, but it doesn't have to be complex. As you can see, this is a real equation. Now, in order to clean up some of the constants in this equation, it's, yes?
Why is it not Vx minus E?
Well, you have to look back at the Schrödinger equation and bring the things to the other side and take care of the signs. It is correct as stated. Check it. Now, we have, in order to do this, and just to write things with a little more clarity, we scale the energy. So we define a calligraphic energy, which is 2m over h squared times the energy E, and a calligraphic V with the same scaling factor. So that the Schrödinger equation then takes the form, the same equation, psi, and I'll use the double prime notation for two derivatives, plus now E minus cal nu of x, psi equals 0. So this is how our equation looks. It's relatively simple and can be treated without carrying constants all over the place. Now, we're going to discuss a few results that are extremely important that you keep in mind for the future. It helps you think clearly. So these results are little theorems that I'm going to state, and the proofs are given in the notes. I will skip some of the proofs, although I will tell you what the strategy is for the proofs, and then show how the theorem implies, as a corollary, interesting things that could easily be misconstrued. So let me give you the first theorem. Theorem 1. This is just the statement that if you're talking about bound states in one-dimensional potentials, there are no degeneracies. So let's write it. There is no degeneracy for bound states of one-dimensional potentials. So it's a fundamental result. We'll see some way to understand it a little later, and you have seen this in 804, I believe. So what is the strategy to a proof? So we want a rigorous proof. So what is the strategy? I will not go through the proof. The strategy is to assume there is a degeneracy. So strategy, assume a degeneracy. So there's psi1 and psi2 different with the same energy. And then you write this equation for psi1 and psi2, and they have the same energy. Then you take the two equations, you multiply the first by something, the second by another thing, subtract it, do a bit of algebra, and you suddenly can prove that. So then prove that one solution is equal to a constant times the other solution. So you do the work, and that's what comes out. Once you've shown that one is proportional to the other, we've declared in quantum mechanics that two wave functions that differ by a constant have exactly the same physics. You can normalize it and normalize them, and the constant could be just a phase, but the phase doesn't matter. So those two wave functions are really the same. So you get a contradiction. You thought they were different, but the difference is just too trivial, and therefore they are really the same wave function, because we've said that two wave functions that differ by a constant should be identified. So that's this theorem, and it's a key theorem.